Hi everyone. My name is Vicki, and I'm really excited to be with you here today at the Go Systems conference, and to be talking about Go routines and really going under the hood. I feel like during this pandemic, some people have been making sourdough or starting book clubs, and I have been watching reality TV and reading the Go runtime source. So I'm very excited to have some fruits from that to share with you all today. We're all Go programmers here, and I think one thing that unites us all is that we really love Go's concurrency primitives. Speaking just for myself, I know one of the things that really draws engineers and engineering teams to the Go programming language is that there's really great abstractions and native support for Go routines, channels, things that make, writing really performant concurrent programs efficient and easy. And of course, if you are also like me, one of the real beauties of that is that Go exposes these great interfaces for us to use. So we really usually don't have to worry about what is happening under the hood. We can spawn Go routines and use channels and know that we're creating lightweight, efficient processes that are able to communicate with each other. And we normally don't worry so much about how that happens because everything runs pretty spick and span. But of course, every now and then you might get to wondering, what is a Go routine? What is really happening when you call Go func and kick off this process? And when I asked this question to myself, the answer that immediately popped into my mind that I'd heard a lot before is that Go routines are lightweight threads. And I think this can be a really useful way to think about Go routines from the perspective of a programmer and a user. But today we're going to delve a little bit deeper to unpack what that really might mean and what Go routines really are. So one thing about this Go routines as lightweight threads framings is that it sort of makes us think about the lightweight Go routine versus the operating system thread. And while this is a comparison that makes sense in some ways, because other languages will directly use operating system threads as modes of concurrency, really when we look at what Go routines are and how they're implemented, we see that Go routines leverage operating system threads. And the way that I've come to think about it is that the Go programming language and the Go routine is providing a really great sort of interfaces with our operating system to be able to leverage things like OS threads, but also provide an even more lightweight and powerful concurrency primitive. So before we delve too deep into any of the details, we'll run through some fast facts about Go routines just to get us started. One thing to note is that Go routines are started and managed by the Go runtime. So another thing that you'll often hear is that Go routines are like user space threads. Because the Go runtime manages them, we don't actually interface directly with the operating system, which is really nice because it means also that Go routines can be hardware independent, since we can have different implementations of Go routines on different architectures, but expose the same interface to the programmer, meaning that our programs can run just as concurrently and easily on a variety of different machines. The other thing that's really great about Go routines is that they're really lightweight. They have really low overhead. Go routines start off with just 2 kilobytes of memory, but they have growable stacks, which allow them to grow and shrink according to the function or the Go routine's needs. The other thing that's really great is that we have really seamless and cheap context switching, thanks to the Go scheduler. And what the Go scheduler really works to do is to maximize efficiency. We want to be sure that as much as possible, we're using all of our system resources, our system operating system threads, to be actively executing Go routines and scheduling off and on any Go routines that are in a blocked state. The other thing that we really love about Go routines, which is sort of the power duo, is that we have native inter-Go routine communication with channels in a way that's memory safe and also works really well with the scheduler to allow us to block and unblock Go routines on channel sends and receives. So in general, all of this makes it so that it's trivial usually to run even millions of Go routines on a given machine. Usually we don't even have to worry about the details as Go programmers, and we can just go forth and spin off our Go routines and be on our merry way. But of course, you're thinking, Vicki, we're now like 5 minutes in, and you still haven't told us what a Go routine is. So now we'll get to the fun part where we get to dive in a little bit to the Go runtime. So within the Go runtime source code, a Go routine is usually referred to by this type G. And we can see here just an abridged version of what the G struct really is, and there's not so much to it. A Go routine has a stack. A Go routine also keeps track of its M, or the operating system thread that it is currently running on. We also have a buffer where we can save some state for the Go routine for when we need to schedule it off or back on to an OS thread so we can resume execution. And then we also have some notion of status. So a Go routine can be ready to run, it can be actively running, or it can be waiting or blocked. We also have a few fields that help us to keep track of the ways that channels interact with our Go routines, namely if there are channels that are pointing into our Go routine stack, or if we're about to park or wait on a channel send or receive, and so we want to be sure that we don't do any unsafe stack shrinking. So with that, you're probably wondering a little bit about how the Go routine stack growing and shrinking really works and what this notion of stack copying is. So to talk about the Go routine stack, like we mentioned before, all Go routines are initially allocated 2 kilobytes of memory. This number has changed a little bit, but is generally supposed to allow most functions to run without any need to grow the stack while also remaining pretty lightweight. And each Go function actually is given a small preamble. And what that preamble does is it calls into the runtime. It sees if there's enough memory to execute, and if we're out of memory, it calls this command more stack. What more stack does is it goes onto the heap, it allocates a new memory segment, double the size of what the Go routine currently has, and then it proceeds to copy over the entire Go routine stack onto this new doubled memory segment and free the old memory. Then we restart execution, and hopefully we have enough memory, but if not, of course, we resume another call to more stack, which doubles the memory again and copies. So effectively, what this means is that our Go routines are infinitely growable. However much memory is needed will just be first allocated and then copied over. With this allocate and then copy strategy, this also means that stack shrinking is really efficient because once our Go routine releases the resources that it no longer needs, those are just freed back onto the heap for the system to use as necessary. So now we can understand a little bit better what's happening here in our Go routine struct, and we see that it's not really so complicated. You know, our Go routines are mainly here to keep a notion of the stack that we need to run and to know what thread it's running on and a little bit of other state. So then we might think, what is the real magic of Go routines? And a lot of it is about when a Go routine runs. We know that our systems have, fixed resources, but we're able to spawn far more Go routines. So a really key part of maintaining efficiency and performance in our Go programs is the Go scheduler. So within the Go scheduler and in the Go runtime, there are 3 key players or key concepts. We have G, who we've already seen, which is our Go routine. We also have M, alluded to a little bit, which is the operating system thread. And then we also have this new player P, which is a logical processor. So one way we can think about these 3 players is that the Go routine contains the code to execute. The operating system thread is where we execute it. And the logical processor, or P, gives us the rights and resources to execute that code on the OS thread. Another important facet of the scheduler is that it is what's called an M of N scheduler. This means that we have M number of Go routines that we're attempting to schedule onto N operating system threads. So the scheduler is responsible for essentially multiplexing these Go routines onto threads, which means also that we can, have an architecture that is independent of the number of threads that we have available, and we're free to basically move around Go routines onto these various resources in the way that the runtime thinks is most efficient. So to go back to our key player here, G, the Go routine, as we mentioned before, Go routines can usually be thought of as being in one of 3 states. A Go routine can be blocked. A Go routine can also be runnable or ready to execute, and then a Go routine can be actively running. So given these three states, we can also think about the scheduler's job as trying to run goroutines as efficiently as possible. So where we can, we want the goroutines on our N operating system threads to always be in the third state of actively executing. So now we have our three players, and we can walk through a couple examples of what happens on the scheduler when we're creating and running goroutines. So in the most basic case, we are just running our function main when we start up our Go program, and main will run on the main execution thread. So here you can see that we have an operating system thread, we have a logical processor P, and then we have a goroutine G, which is running our main function. Then what happens is that we'll actually create all of the processors that we need. And the number of processors created by the runtime is going to be equal to the number of logical cores on your machine, which you can see in the Go environment as this variable Go max procs. So now let's say that main spawns a Go routine. What then happens is that that Go routine will go and wake up an idle processor. This processor will then create an operating system thread for it to run goroutines, and then schedule that Go routine onto the thread and begin to execute. Now let's say that our Go routine is finished executing, so now our thread and our processor are idle. So they go back into holding to wait to be used to schedule and run further Go routines. So with this example, you might be wondering what we really need this processor P for. It seems like we're just mapping Go routines onto threads, and there's no real need for this other player. But we really need P to keep track of a notion of what Go routines to run in the case where there's more work to be done than there are resources on which to do it. So let's say that this is the state of our world. We have two operating system threads, two processors, and two Go routines happily executing. Now our main function spawns a new Go routine, and we need to find a place for it to live. What happens is that we queue this Go routine onto the local processor and add it to what's called the local run queue. So one of the really important functions that these processors play is that they maintain an idea of what Go routines have yet to be run in their local run queues. Then when G1 finishes executing and the processor is available again, it looks in its local run queue for a G to run and then schedules that onto the OS thread to begin executing. So Ps are really important because they know what Go routines are available for an operating system thread to run. So now we've talked a little bit about how we schedule running Go routines that are all ready to go, but a really important part of the scheduler is dealing with blocked Go routines. And importantly, since we want to maximize execution time on operating system threads, one of the scheduler's really important jobs is to move blocked Go routines off of operating system thread resources and then bring them back on once they're ready. So we're going to walk through three of the main cases in which this happens. So there are many things that can block Go routines, but some of the most common things are system calls, network I/O calls, and channel operations. So to first talk about blocking system calls, let's say that this is our world. We have one operating system thread that is happily executing its Go routine G. And this Go routine G then makes a blocking call, a blocking system call, which invokes the runtime scheduler. Now G is in a blocked state, and what happens is that our processor P0 releases the operating system thread that is executing G's blocking system call. So then P0 needs some OS thread to continue executing these Go routines that have just been added to its run queue. And so it goes ahead and wakes up this thread M1 and continues execution. Now when G0 unblocks, M0, our operating system thread, needs to find a processor to continue running. It wakes up this processor P and then continues to execute. Now, in the case where our thread can't find a P, there are no processors available, then the thread goes to sleep, and our Go routine is added to what's called the GR queue, or the global run queue, where processors can look if their local run queues don't have any Go routines. So what's really neat in the way that the scheduler handles blocking system calls is that it allows the blocking Go routine to hang on to the operating system thread that's executing the system call, but we also swap it off of the processor so that resource is available to run other Go routines. And of course, you might be thinking that this is a lot of work to be doing, this switching on and off. While it's much more efficient than context switching OS threads, is still not no overhead. And since some system calls are quick, the Go runtime actually does a slight optimization where it only does this context switching for system calls that it thinks will be quite expensive. So now we can think about how the Go runtime might handle network calls. Now, of course, network calls are a kind of system call, but importantly, they are asynchronous. And if we think about how we commonly handle network I/O as Go programmers, usually the net package provides a default of spawning a Go routine to handle each incoming connection. And within Go, we can often interact with these network requests in a blocking interface, which makes our lives as Go developers really easy. And the way that this blocking interface is exposed is thanks to the work of what's called the net poller. And the net poller's job is to schedule Go routines that are waiting on these asynchronous system calls, which provides that blocking interface in Go. So to talk a little bit more about what that means, let's say that we have our one happy operating system thread running a Go routine with a couple more scheduled. Now G0 wants to make a network call. And of course, it goes into a blocked state now since we were waiting on that network I/O. Now we introduce the net poller. And what the net poller does is it has its own operating system thread, and it handles these events from Go routines that want to do network I/O. The net poller interfaces with the operating system that you're running on to pull the appropriate network sockets, and then it reschedules Go routines when their network resources are available or when they're unblocked. So to dive in a little bit to how this works, netpool is essentially an interface that is implemented in various different architectures that Go runs on. And there are a couple of different functions in the interface, but the most important one for our purposes is this net poll function. And what it does is it pulls the network and it returns a list of Go routines that are now ready for execution. Then what happens in other parts of the runtime is that we regularly call this net poll function and inject the list of Go routines that are ready back onto resources that are about to be scheduled on our processors. So G0 is moved to the net poller when it wants to make a network call, where the net poller will then begin to regularly pull the file descriptor for the network resource that G0 is trying to access. And then this frees up our processor and OS thread to then schedule G1 and begin to execute. Now, later, when the net poller adds G0 to our list of executable Go routines when the network call is complete, the G0 Go routine gets moved back onto the local run queue, where it can then be scheduled for execution on our OS thread. So this is really neat. We don't need to spawn new operating system threads or new processors to handle these network calls. And this also exposes a really nice interface for us as programmers where we can think of network I/O as blocking within our Go routines, but the net poller handles the asynchronous part of that, exposing this really nice interface. So now we'll talk a little bit about blocking on channels, one of our other favorite concurrency primitives. And channels are great because since they are built also in Go, channels have really good insight into what's happening in a Go routine, which allows them to schedule Go routines really efficiently. So again, here is our world. We have an operating system thread running one of our Go routines with a couple in the queue. And now G0 wants to do a send on a full channel. And this is blocking since our channel is currently full. Within the channel struct, we have this notion of a receive queue. And what the receive queue is it's actually just a list of Go routines that are blocking and waiting on a channel receive to happen. So in this case, we add G0 to the channel's receive queue, and the scheduler, because G0 is blocked, removes it from M0 and begins to execute the next Go routine. Now let's say that this Go routine G1 is our savior. It's doing a receive on this channel. And so when that channel receive happens, the channel looks into its receive queue, sees G0, then we can make G0 runnable and add it back to our local run queue. So all of this happens really seamlessly by leveraging the channel struct and calling into the scheduler when channel resources become available and unblock our Go routines. So we walked through some examples of how we schedule different work, and we'll add on sort of one bonus feature of the scheduler, which is how it implements work stealing between threads. So we might be in a case where we have two threads that are both have somewhat healthy queues and are executing, and we might get to a case where one of our threads finished executing all of its Go routines faster than another, but there's still work left to be done. And in this case, of course, we want to redistribute work so that all of our resources are constantly executing. So what happens here is that P0 tries to steal work from another P. So we only have one other processor, so P0 goes ahead, looks in its local run queue, and steals half of the work for itself, and then begins to execute. This ensures that threads don't remain idle while there's still work to do, and effectively redistributes load between our processors and our operating system threads. So now we are Go routine experts a little bit. We know that the Go routine stack is lightweight and growable. We know that the runtime scheduler uses M of N scheduling to allow for really efficient use of our operating system threads. And we know a little bit more detail how we handle long operating system calls, networking syscalls, and channel blocking all really seamlessly in the scheduler. And hopefully we've come away with a little more understanding of the sort of convenient and really nice blocking interfaces that are exposed for us to use as Go developers. So I'm so glad for you all for sticking with me through this adventure into the Go runtime and understanding how Go routines work. Hopefully you've come away with a little more knowledge. I know I've come away with a lot more appreciation, and thank you all so much for your time.